Non-renewable energy and electricity. First, let's define energy so we're all talking about the same thing. Primary energy is the energy found in natural resources like coal, oil, sunlight, wind, and even uranium. It's the stuff you pull up out of the ground that you can create energy from through a process called energy conversion. When it's converted, it's turned into what's called secondary energy. And finally, end use is the energy that is created from the secondary energy sent out to the consumer. Some primary energy sources are better suited for certain things. 80% of coal is used to produce electricity, and only 1% is used in transportation. 65% of oil is used for transportation, and less than 1% is used to generate electricity. 35% of natural gas is used to generate electricity, and most of the rest is used for cooking, heating, etc. The second law of thermodynamics states that no energy conversion process is 100% efficient. There's always some heat loss. That brings us to our first question. What's the first law of thermodynamics? The answer? The first law of thermodynamics, also known as the law of conservation of energy, states that energy can neither be created nor destroyed. Energy can only be transferred or changed from one form to another. Yeah, I didn't know this either. I mean, I knew it, but I didn't know it was the first law of thermodynamics. Energy end-use efficiency. That means the rating for all the conversion processes from raw natural primary source to final end use. What this graphic basically explains is how much energy is lost from the raw material down to the end user application. All right, so if a lump of coal is 100 energy units, by the time it gets to that light bulb running electricity, it's down to 1.2 units. A lot of energy is lost in the conversion processes that it goes through. That's basically what it's saying. It's very inefficient. Question 2. Are LED bulbs more efficient than traditional incandescent bulbs? The answer is, of course, yes. Since they use only a fraction of the wattage to power them, and they give almost no heat, they are very efficient. According to the U.S. Department of Energy, adoption of LED bulbs would save hundreds of millions of tons of greenhouse gases from entering the atmosphere, because so much less energy would need to be produced to power them. And there's a link there if you want to go check it out and see if my math is right. Non-renewable energy means that the sources are used faster, in some cases much, much faster, than they can be replaced. The short version, they will run out eventually. Sources like coal, petroleum, and natural gas, as well as nuclear energy. Renewable energy comes from sources that don't run out when they are used, such as sunlight and wind, or they can be replenished like wood. Almost 80% of the world's energy use comes from burning fossil fuels like oil. Nuclear energy accounts for about 4%. Burning wood and charcoal, mostly in underdeveloped countries, accounts for about 7%. Renewable sources like solar, wind, biofuels, etc. make up less than 10%. Basically what this graphic shows is a pie chart delineating all the numbers that I just read. Long story short, we use coal to create energy that we consume, far and away more than anything else. Reserves. Energy sources that can be exploited. Production. The amount of energy that can be produced from those reserves. Consumption. The amount of energy actually produced and consumed. For example, the U.S. produces almost 3.5 billion barrels of oil in a given year, but the U.S. consumes over 7 billion barrels of oil in that same year. Our consumption outpaces our production, so we must buy it from elsewhere. Proved reserves. The amount of energy resource we know about and can get at using current technology. The reserves to production ratio, R/P. How long that resource will last using current tech. For example, there's about 1.7 trillion barrels of oil known on our planet. We use 33.5 billion barrels a year. That means in about 50 years we'll run out if no new sources are found. So the RP ratio is 50. Natural gas has an RP ratio of about 53. Coal is about 110. But it's still nasty, dirty, and terrible for the atmosphere. Energy return on investment. EROI. How much the energy resource is worth divided by how much it costs to get at it. Finance or business majors, you know that if it costs more to dig it out of the ground than it makes, it's just not worth it. The bottom line here is this. Use of fossil fuels is the biggest contributor to adding more greenhouse gases to the atmosphere than we can handle. Nuclear energy is clean, but comes with its own hazards, like the damage done to the environment by digging the uranium out of the ground, not to mention storage for all those highly radioactive spent fuel rods. The environmental costs of using non-renewable fuels are vast and often ignored when considering the cost of these fuels. Coal. Humans have been using coal for over 5,000 years. There seems to be enough of it to continue to power about 29% of the world's energy needs for the next 100 years. Coal mining is bad for the air, the natural landscape, and the groundwater. But tech advances have addressed some of these problems and show potential to solve more. The term clean coal is a marketing term that is completely made up. There's no such thing as clean coal. The current tech just doesn't live up to that hype. 300 to 400 million years ago, the planet was covered with thick, swampy forests. As plants died, they sank into the ooze and got covered with sediment. Partially decayed stuff is called peat, which is still used around the world as a home heat source. And just because it's interesting, here's a link about peat from BBC News. Anyway, over time, the pressure from the sediment becomes intense. It squeezes out the water and traps the carbon inside, forcing the transition to coal. Lignite. It's younger and has survived less pressure than other types. Softer too. 25 to 35% carbon, yielding 3 to 4.5 kilowatt hours of energy per kilogram. Anyone here that has ever watched a movie about drug dealers knows that a kilogram is 2.2 pounds. So there you go. Subbituminous, 35 to 45% carbon. Bituminous, much denser than these other slackers. Anywhere from 45 to 86% carbon, 5 to 8 kilowatts when burned. Harder and less pollutant filled than lignite and subbituminous. Anthracite, 86 to 97% carbon, more than 8 kilowatts when burned, much less common, only found very deep. Harder and less pollutant filled than lignite and subbituminous. So anthracite is the rock star of coal, but it's still hard to find because you got to go deep. Less than half of the world's coal is the desirable bituminous and anthracite varieties, 45%. The rest is lignite and subbituminous. EROI is calculated on a case-by-case basis depending on the depth of the seams where the coal is found, cost of digging it out, trucking it off, etc. In a given year, 7.8 billion metric tons were dug out of the ground, making the reserve to production ratio 114. Even with that amount being dug out globally, scientists still think there's enough coal to last 100 years or so. And that brings us to question 3. Where does most of the world's coal come from? Answer: the U.S. leads the way with the highest amount of coal production. The leaders in coal production are the United States, Russia, China, and India. The graphic here shows a breakdown of how much coal is dug out of all these different countries. The United States killing it. Remember, Europe, although Europe is higher on the chart, Europe is made up of a whole bunch of different countries. So from a single country standpoint, the U.S. rocking the coal market. Most coal in the U.S. is used for electricity production. This is a big jump from 50 years ago, when more than half of it was used to heat homes. Ask your grandparents, they'll tell you. Now, most U.S. coal is used in power plants to boil water. The steam is pressurized and used to turn turbines, which create electricity. The exhaust is passed through a scrubber, which is used to capture the pollutants and noxious gases. Then the clean steam is released out through the smokestacks. In the older plants, energy conversion produced about 25% of the coal's energy. The rest was lost during the conversion. Modern plants have that number up to almost 40%. 40. Coal mining is hard, dangerous work. Cave-ins, dust, floodings, and explosions make it a tough, dirty job. Around the world, almost 1,000 people have died from it last year alone. Strip mining and mountaintop removal make it hard to justify. Often the debris sulfides end up making sulfuric acid when mixed with the oxygen in the air and polluting nearby streams and waterways. Mercury and other toxic chemicals enter the waterways and grounds surrounding coal mines, settling into the internal tissues of animals, including humans. This causes many health issues, including neurological damage. Coal contains nitrogen and sulfur. These are released when coal is burned and become nitrogen oxide and sulfuric acid. Scrubbers are constantly being updated with modern versions cleaning the coal before it is burned. However, a common 1,000 megawatt coal-fired power plant still produces the same amount of carbon dioxide, a particularly bad greenhouse gas, as 2 million cars. In the next 10 years, global demand for the energy that coal produces is expected to double. The amount of CO2 that will be put into the atmosphere will be more than we have added from the beginning of the Industrial Revolution till now. What does this mean? That's right. We're all gonna die! But not before somebody makes some more money off of us. And that brings us to oil. The first commercial oil well was drilled in 1859. In 100 years, oil outpaced coal as the leading source of energy worldwide. But oil isn't distributed evenly around the globe. Some places have more than others. And it is finite. It's going to run out as demand goes up. Oil and natural gas are less dense than water, so it tends to float up towards the surface. Sometimes it makes tar pits. Sometimes it'll get trapped under impermeable rock, forming a reservoir. These are not underground lakes of oil, though. They're layers of porous rock with little drops of oil in all the holes, like the way a sponge holds water. Those are called conventional reservoirs. There are other non-conventional deposits, like those found in shale, which is a kind of sedimentary rock, and tar sands, like those found in Canada, Kazakhstan, and Russia. In order to form a reservoir, 3 conditions need to happen. A shallow sea with lots of organic stuff that has died and sunk to the bottom. After it had been compressed for a couple of million years and turned into oil, that oil must rise up into a porous rock layer. That porous rock layer must be covered by a layer of rock that is not porous, so it keeps the oil from reaching the surface. Most of these reservoirs on Earth are in the Middle East. Some are in Venezuela. Canada has some tar sands, and the U.S. brings up the rear about 2% of the world's supply. Peak oil. Peak oil means the absolute most an oil field can produce. After this amount, production can only go down. More numbers. Over the past 100 years, we have consumed about 1.2 trillion barrels of oil worldwide. Estimates say we have 1.7 trillion on the planet. We produce 33.5 billion barrels a year. This suggests that the reserve to production ratio is just under 51. So we have about 51 years worth of oil left at this rate. But consumption is going up. If more oil is found with new, better tech, we may have more, like 2 or 3 trillion barrels more. Natural gas. Again, most of it is in the Middle East. Lots more numbers here. Suffice to say, we have about 53 years worth of supply left at the current rate of consumption. If the tech to find it and extract it improves, maybe we'll have more. Oil production. Oil is drawn up out of a reservoir in 3 steps. Primary oil recovery gets about 20% of the oil in a reservoir. Secondary oil recovery gets another 10 to 20%. Tertiary oil recovery gets out another 10 to 20% by injecting CO2 or steam into the well to help with the flow. Still expensive, but doable. Hydraulic fracturing, or fracking, is another method that is similar. High-pressure liquid is mixed with sand to blast open cracks in the rock to allow oil and natural gas to flow. Refining crude oil. Crude oil is made up of lots of different types of molecules, all with different boiling points. Crude oil is heated in distillation columns called cracking columns. The low boiling point stuff evaporates and rises to the top of the column, where it condenses into what will become gasoline and jet fuel. The higher boiling point stuff condenses near the bottom of the column. It will become fuel oil, lubricating oil, and asphalt. About 15 to 16% is turned into non-energy products like fertilizers, pesticides, and plastics. Over the last 40 years, the amount of oil production used for heating homes and businesses has been reduced by half, from 15% to around 7%, because of a rise in the use of electricity and natural gas. Oil, natural gas, and the environment. Oil is big business, and it has its politics too. A single oil field in Saudi Arabia loads 10% of the world's oil onto tankers every day. An attack on such a process would have serious political, environmental, and economic repercussions. That must be why we have Marines stationed there. Natural gas is better for the environment than burning oil, but with 600 million cars and trucks in the world, there won't be any slowdown in oil production anytime soon. Natural gas burns much cleaner, even in plants producing electricity. Power plants burning natural gas release about half of the CO2 and other greenhouse gases that they would if they were burning coal. Methane escaping is still an issue. Most of natural gas is methane, with a few other trace gases thrown in, like propane. Makes you wonder what Hank is doing back there. Unburned methane is much worse as a greenhouse gas, 25 times worse. Accidents involving natural gas can outweigh any potential benefits. That brings us to nuclear power. Burns clean, generates a tremendous amount of energy, and emits very little greenhouse gas. So what's the problem? Meltdowns around the world have raised concerns over contamination of people and our planet by radiation. Nuclear energy creates nuclear waste, which is incredibly toxic to life in general and unsafe to store anywhere. And don't you want to know how it works? How does it work? When a uranium atom is split, it releases neutrons powerful enough to split other atoms. This continues in a chain reaction that, if left uncontrolled, delivers an explosive force far beyond any other device created so far. In a nuclear reactor plant, the reaction is controlled, and the heat that is released is used to heat water into steam, which drives turbines which create electricity. Uranium is fairly plentiful, and as technology for extraction improves, it will become more and more economically feasible to mine it. Most of it comes from Australia, Kazakhstan, Russia, South Africa, and Canada. Some countries there that might need some freedom. The worldwide reserves are good for another 100 years. Uranium is rarely found in big deposits, so large areas need to be mined for small amounts. Once it's found, uranium is ground up into a fine powder and washed to remove unwanted minerals. What's left is called yellow cake. The yellow cake is put into centrifuges that separate the atoms that have 238 neutrons from the atoms that have 235 neutrons. These are the ones that get used. The material is then formed into pellets, which are packed into fuel rods. Next, between 100 and 300 fuel rods are placed in a power plant's reactor core, where fission, the splitting of atoms, takes place. Nuclear power plants operate much like power plants that use fossil fuels, except the water is boiled with heat from a nuclear reaction instead of heat from burning fossil fuels. Nuclear power and the environment. Water flowing through uranium mine debris fields gets acidified, and that has negative effects on nearby lakes and streams. Another problem, heat. It usually gets vented through big cooling towers. Those towers have come to symbolize nuclear power. That heat gets dissipated in rivers, or lakes, or nearby ocean waters, where the elevated temperatures can be very harmful to the quality of biodiversity in those areas. Even though the rate of the reaction isn't enough to make an explosion like a bomb, if the core overheats, it can melt down. If the buildings that are designed to contain such an event fail, contamination of huge surrounding areas where people live, could become contaminated. Spent nuclear fuel. One big problem with nuclear energy is what to do with the fuel rods when they are spent. Over time, fuel rods get worn out and no longer produce sufficient heat. They do, however, remain radioactive for millions of years. They can't just be tossed into a landfill or into the ocean. They must be buried in stainless steel casks or submerged in internal pools of water. Spent fuel rods can be recycled using, you guessed it, fuel recycling. This increases the level of plutonium in the fuel, which, if it falls into the wrong hands, can make for a very bad day for a very large number of humans. Plutonium is easy to use to make a nuclear bomb. It is fair to say that no primary energy source generates more controversy and debate than nuclear power, especially in the United States. Because of high construction costs and widespread public resistance, no new nuclear power facilities have been built in the United States since 1978. Basically, this article outlines the political ping-pong of burying nuclear waste under the Yucca Mountains in Nevada. The debate was stopped when President Obama halted it. The Trump administration okayed it, but that was apparently without the president's knowledge. He has since halted it again. The debate rages on. Because the people in Nevada don't want it there. Electric power generation, distribution, and use. About 40% of global primary energy supply is consumed to generate electricity. The most important primary energy resources are coal, natural gas, nuclear, solar, wind, and flowing water. Electricity may also be generated by chemical reactions in batteries and fuel cells. The relative contribution of each of these sources to the total amount of generated electricity is influenced by patterns of availability, economic costs, and environmental impacts. Generating electricity. Electricity is comprised of charged particles flowing through a wire. The current is measured in amps. The amount of current is measured in volts. Like water in a river. The amount of flowing water is like the current. The gravitational pull on that water is like the volts. The rate that energy is converted from one form to another is power. Power is measured in watts. 1,000 watts is a kilowatt. Batteries create electrical energy from chemical reactions. Fuel cells create electrical energy from reactions between hydrogen and oxygen. Electric power is produced in a central location and then transmitted out to customers. Transformers have high voltage, anywhere from 230,000 volts to 760,000 volts. The energy is then converted back to a lower voltage before reaching the average home, which runs on 110 or 120 volts. Most power plants were designed to burn non-renewable fuels to generate electricity. Plants that use renewable resources like wind and solar usually generate less power and are more widely spaced out. Redesigning power grids to take advantage of these sources is a major challenge in the transition to renewable sources of energy. The environmental impacts. Since over 50% of power plants burn coal, the negative impact from mining and burning it to produce the level of energy we need is more than double that of natural gas, and 10 times more than any renewable source. Coal is bad for the environment in lots of ways, from mining it to refining it to burning it. All batteries, no matter how they are made, will eventually have to be discarded. They end up in landfills, and while they only make up less than 1% of total waste in landfills, their contents, being mostly heavy metals, make up almost 75% of the pollution. Fuel cells using hydrogen are better, but the cost of them producing the energy we need is high, and current tech isn't cutting it economically. Electrical transmission creates electromagnetic fields around the lines, and there has been, and continues to be, debate as to the negative effects of these fields. Also, the coolant that was used in transformers contained PCBs, which have a wide range of toxic nastiness for humans and animals. They have since been banned, but they don't break down very well and continue to wreak havoc on ecosystems in many places. My 5 fun facts. Combined, the technical potential of the major renewable technologies, wind, bioenergy, geothermal, and landfill gas, could provide 5.6 times the amount of electricity this country needs. Organic material in landfills decomposes and forms a gas that can be captured and used to generate electricity. And I bet it smells good too. 31 states have the potential to generate about 1% of their electricity this way. Anaerobic digestion is also technically proven for conversion of organic waste to biogas, principally methane. The process can be used to produce significant quantities of gas from manure, sewage, or a mix of sewage and solid wastes. The terms bioenergy and biomass refer to a wide range of natural materials. All of the materials contain the terms bioenergy and biomass refer to a wide range of natural materials. All of these materials contain energy that can be used to generate power. Creation of an economic level playing field is probably the single most important step that could be taken to promote renewable energy. And that's it. So now you know everything there is to know, or everything at least that I know, and everything that was in the book about renewable energy and electricity. If you haven't read the chapter, go ahead and read it. It's a little dry, it's a little dense, but the information you pull out of it is kind of fascinating.